Okay. Good. Mm-hmm. Great. We're getting going. Let me just grab my headphones. 1 second. Where's my headphones? Can't find my headphones. Where would they be? Oh, well, I guess I'm got a backup pair right here. Just override the microphone. Doop-a-doop-a-doo. All right. Merry Christmas if you're watching. Okay, trying something a little bit new today. I'm trying streaming via Zoom because all of these streaming apps, evidently having a PhD is not enough to understand how they work. So let's see here. How am I doing on sound? Do a quick sound check. All right. Okay, I'm gonna watch this. So today I want to watch this video from Europe's the causal version of principle of insufficient reasoning. Advanced sharing. I want to share my screen here. Here we go. Oops. Nope, it's not what I want. Here we go. Yeah. Causal version of principle of insufficient reasoning. So this was talk given by Dominic Jansing at the causal modeling workshop in NeurIPS. And while we're at it, let's put on some Christmas music. My King Wenceslas. There we go. Oh, We Three Kings. I like that one. Turn down the volume. There we go. There we go. All right.
Equally likely. Hello, I'm Dominic Jansing.
Oops.
Of insufficient reason and maximum entropy. The idea is that statistical inference is incomplete until today because it requires additional causal principles. And these principles to be added is something I would call laws of abstract physics or hardware-independent physics.
Hardware-independent physics.
And I will start with the principle of insufficient reason, as
Let's get a preview
phrased by Ben.
I've seen this before. Let me just Google this. Principle of insufficient. Something called sufficient reason. What is that? Principle of sufficient reason states that everything must have a reason or cause. So I suppose insufficient reason would be, well, I'm not sure it would be the converse of this, but the modern formulation of the principle is usually attributed to early Enlightenment philosopher Leibniz, although the idea was conceived of and utilized by various philosophers who preceded him, including Anaximander, Parmenides, Archimedes, Plato, Aristotle, Cicero, Spinoza, Aquinas. Notably, the post-Kantian philosopher Schopenhauer elaborated the principle and used it as the foundation of the system. Some philosophers have associated the principle of sufficient reason, with ex nihilo nihil fit. I'm not really good at Latin, sorry. William, what does that mean? It's a thing. Nothing comes from nothing. Great. William Hamilton identified the laws of inference modus ponens with the law of sufficient reason, or reason of reason and consequent, and modus tollens with the contrapositive expression. Okay. Something more formal here. The principle has a variety of expressions, all of which are perhaps best summarized by the following. For every entity X, if X exists, then there is a sufficient explanation for why X exists. For every entity E, if E occurs, then there's a sufficient explanation for why E occurs. And for every proposition P, if P is true, then there is some sufficient explanation for why P is true. Great, so we have a principle of sufficient reason. So I don't think insufficient reason turns up much. Let's see. Principle of indifference. The principle of indifference, also called the principle of insufficient reason, is a rule for assigning epistemic probabilities. The principle of indifference states that in the absence of any relevant evidence, agents should distribute their credence, degrees of belief, equally among all possible outcomes under consideration. So what Bayesians might call a non-informative prior. Oh, I anticipated it. Oh, great. That's awesome. In Bayesian probability, this is the simplest non-informative prior. The principle of indifference is meaningless under the frequency interpretation of probability, in which probabilities are relative frequencies relative degrees of belief. Okay, so interesting that. So so this is right here inside this Bayesian statistics little module within Wikipedia. So cool. So principle of indifference is absence of any evidence. We start with an uninformed prior, or non-informative prior. Close some of these other windows here. Great.
Bernoulli and Laplace, and also called principle of indifference by James. It reads, assign equal probabilities to all possible outcomes under consideration if there is no evidence for preference to any of them. So knowing only that there's one ball in one of the n urns, one assigns probability 1 over n to each case. And this subjective probability reflects the symmetry of the problem. It defines an uninformative prior in Bayesian inference. But I'm trying to argue that we need a causal principle of insufficient reason instead. To see this, we consider the following mechanical device. It's made of tubes. You see this tubes with 3 entries, 1, 2, 3, and a ball entering from the top. If the ball takes the first entry, then it has 2 options later for y. If it takes entry 2 or 3, it always ends up in y equal to 1, so exit 1. So you can easily see that there are 4 paths that are possible. But would we really consider all 4 paths equally likely? Because this would amount to assigning higher probabilities to entries that enable more options for the exits.
Makes sense.
I think it's more plausible to consider all entrances equally likely. And given that entrance X is equal 1, we would consider both remaining options for the exit equally likely, which results in assigning probabilities 2/3, 1/6, and 1/6 to the 3 possible exits. And you can easily see that the device is symmetric with respect to X and Y. So the asymmetry of this distribution over the paths is based on the causal direction, just by the knowledge that the ball enters from the top and not from the bottom. More generally speaking, the causal principle of insufficient reason reads, assign equal probabilities to every option for the cause, because knowing about the mechanism relating cause to effect is irrelevant.
See, to me, this is one of those things where you ever get that feeling when you're learning something or you're kind of seeing a new concept, and the toy example is so simple as to be almost absurd. Like, yeah, okay, equal probability that's of X being 1, 2, or 3, but then since Y is conditional on X, we're going to have to give different probability to Y given X, and because Y is clearly dependent on X, I'm not even sure why you need causality or you need causal semantics to kind of parse that out. I mean, clearly this is a causal system, but yeah, it's just like I'm afraid like this is all of a sudden going to get like, oh my God, this is tough. I'm not really sure where it's going to come from. But let's see what happens. It's kind of okay, yeah, obviously
relevant at this point. And then assign equal probabilities to every remaining option for the effect given the cause. And a more abstract version is the following that we will need later. Given two variables.
Let's dive into this abstract thing here. So given two variables with finite range, given the knowledge that X causes Y and that causal mechanism only allows X, Y in space of real numbers, or let probability of X be a uniform distribution over all X allowed by R, and for any X, sorry, so we're putting a uniform uninformed probability over all the X, and then for any, so okay, so this is interesting. So we're now talking about we don't know what the marginal of X is, and so if we had to be Bayesian about it, we would just put in an uninformed prior on X, but not on X and Y. For any X, let the distribution Y given X equals X be uniform over all Y within each value of X. Okay. Then the causal principle of insufficient reason reads that the probability, what does this notation mean here? Oh, okay, it's just the factorization, probability of Y given X, and probably which is the joint distribution, is not uniform over R. Yeah, it's interesting. Yeah, that makes perfect sense to me. I guess those are the best, maybe those are the kinds of the best results.
XY with finite range.
Like when something is just so obvious that they state it in a way that it seems like you feel like you already knew it, but all of a sudden we're talking about being Bayesian over the joint probability of a causal system where maybe we didn't know what that was. We didn't know what that those probabilities were, or that joint probability distribution was. So that could be important.
And given the knowledge X causes Y, and the knowledge that the causal mechanism only allows xy pairs in some subset R of the Cartesian product of x and y. Then we assign a uniform distribution over all x that are allowed by R, and we construct a conditional prior for y given each value of x as the uniform distribution over all remaining options for y. And then the causal principle of insufficient reason prior reads, it's just the product of p of y given x and p of x constructed as above, which is in general a non-uniform prior over R, which captures the asymmetry between cause and effect. And once we have defined such an asymmetric prior, we are able to infer causal directions with some probability by just comparing the corresponding likelihoods.
Okay, so that was a huge jump. So now we just use some kind of Bayesian reasoning to reason about causal direction in a bidirected edge in a two-node relationship using just this idea. Okay, so let's make sure I didn't miss.
As the uniform distribution over all remaining options for y. And then the causal principle of insufficient reason prior reads, it's just the product of p of y given x and p of x constructed as above, which is in general a non-uniform prior over R, which captures the asymmetry between cause and effect. Once we have defined such an asymmetric prior, we are able to infer causal directions with some probability by just comparing the corresponding likelihoods.
Compute p of x given, so we compute it, so we statistically estimate. So this is the joint, and we look at, wait, hold up, what is, this is just p of y given x times p of x. And this is p of x given y times p of y. I wonder why, wouldn't they just be the same if I estimated them from data? And for x, is if I suppose, well, oh, I see. So I guess the idea is that if I, oh, I see. If I assign this a, okay, so what I'm doing here is I'm looking at the likelihood of x and y under, you know what, we can test this out. I want to test this out right now. This could be pretty cool. So I think what he's saying is that if I, I think what he's saying is that if I assume just a prior of both these models and evaluate the likelihood, assume that uninformed prior in both of these cases where jointly they become it's not a flat prior, like together, it's not, you know, so in this case, if we assume they're uniform, that together this p of x times p of y given x are not uniform, and then we could kind of figure out which way direction goes by just looking at the likelihoods under both of those models. I'm going to test that out right now. Very simple to test out. Let's just do that. All right, just gotta share my. I'm just cracking open my IDE over here. I think I'm going to use R. All right. I'm going to share my other screen here. How do I share screen? New share. Got too much stuff open as usual. Here we go. All right, so we got, let's say, so I want to find some where there's some kind of ground truth distribution. So this is, can I do this without? Let's do this without packages and just look at. No, I'm gonna use BNlearn. All right, so let's find some continuous distribution to reason about. We can write one. So let's say X is, I don't know, our gamma. Let's do 100 of these. I don't know, 2, 4. What's that look like? Okay. And then Y is, I don't know, something. See, the trouble is, I don't think that BNlearn can handle continuous uniforms very well. So let's use just use a categorical distribution. Yeah, okay, so let's do 100 of these, mean of, I don't know, 4. Okay, and then, all right, so we have nothing exceeding. And then Y is, I don't know. To just something nonlinear. And 2x plus, no, let's do the polynomial function plus 2. Forget 2, let's do times x. There we go. This. Max y. So I'm going to just get the range here so I can put a uniform on at least some fixed range of numbers using uninformed priors. So let's try that now. So I need to fit a Bayes net. I'm going to do that with some. I need to give it its own distribution. Let's try, first off, let's net. Let's go x2y is to network x, y given x. Check that real quick. All right, so I need to figure out how to get this thing. I forgot how to do this. I need to turn it into a generative model. Custom. Custom fit, maybe. All right. So we gotta fit this. Let's just use this thing here. We got A, B, C given A. All right, so something like this. Oh, come on. So we want to give it a uniform distribution on. All right, so let's just do 0.5, 0.5 for two binary outcomes. Low and high, that sounds good. I'm gonna make that for X. For Y, well, I guess we can use the example he just used. So that'll be one. So each X has 1/3, 1/3. I should make these categorical, shouldn't I? How do I do that? Oh, I see. So let's actually map this. So instead of using these random discretes, we'll go back to the actual. But let's get this set up first. So I'll redo this. This is wrong. But what I want to do is construct some categoricals here. So what is this? What did he have? Why is one, 2, 3, and then here we want so y given, so we have to actually we'll have to do it like this, I think. I'm not even sure if I'm matching these up correctly. What is this thing? This is not a very straightforward way of fit. All right, we got A, B, and C. So these last two dimensions. True, false. So the first thing should be 1, 2, 3. I'm gonna have to play around with this until I figure out what the right kind of variables are here. This will be y. X here will be same thing. And then X2Y model, custom fit, X equals CPT X, Y equals CPT Y. So let's try. See this. So we need to give you some values here. So X. So I don't know what the ordering is. I'm going to guess this is just going to be. Because we need one for each level of X. So when X is 1, we'll have 3 has a 1 has a probability of 0. 2 has a probability of 0.5. 3 has a probability of 0.5. When X is 2, 1 has a probability of 1. The probability of 0 has a probability of 0. And when X is 3, it should be the same. Dimensions of CPTY should be 2, that'll be 3. Or is it 2? Shoot. Yeah, okay, let's try that. Mess it up. Number of columns equals. Why is that happening? Number of rows. It's been so long since I worked from agencies. You should definitely have 3 columns. Okay, let's look at that. Okay. This is going to be a bit dodgy if there was. I guess we'd have to have 3. PTY 011.5. I guess if we're summing into columns, let's see how that looks. So what we have here, the dime names. Well, let's just name it, see what that looks like. CPTY. So for I being 1, 2, 3, sum to 1, sum to 1. For 2, so X is 2. We always get 1. X is 3, we always get 1. Great. Okay, and then for this one, well, let's see if it works. Great. So let's actually look at X2Y model X. All right, we got third, and here. Okay, it looks right to me. When X is 1, we get 2 or 3, probably 0.5. Otherwise, we get 1 for. So, okay, so what we want to do next. This is our model 1, and this is the model that we think is going to be right. We're putting we put a uniform prior on X, and then I guess something like, so given. So is that what he's? You put it. uniform. So maybe this is the ground truth model. So let's try see if I can't get rid of this nonsense. Let's see if I can't. So I don't think this is that is definitely not a uniform over y for each value of x. Over y. For any x, let probability of y given x be the uniform over all y. Actually, I'm not sure I follow this. Let p of x be a uniform over all the x, and then given any for each x, we'll get a uniform for all the y. Turn this volume down on this music here. Yeah, I'm a bit confused over not uniform. How is that not uniform? Huh. So we have, this is like starting from without looking at it, we have two variables. We have some knowledge that x, given knowledge that x, so we know that x causes y. And that's the causal mechanism only allows x and y. So is this some subset? Okay, so this, yeah, so the constraints must be uniform over the values that are allowed here. Okay, so we're putting a uniform here. So, all right, so let's, oh, I see. Okay, so we have a uniform over the values allowed by, so we have a uniform over x. We have a uniform over values allowed by, values of y allowed by x. And so we could say, we could, for example, have a new model. This is the ground truth. So this model one, you're gonna have a ground truth that's maybe, then, so let's say that here we're 0.2, 0.2, 0.6, for example, and then here we're, I don't know, 0.8, and then 0.2. So this could be, so we're still staying within the allowed values, but these might be the ground truth values allowed therein. While this is our this is our model in the right direction. So what is, so what would that look like? So if we said, now we're going to have the wrong model. We have, it's going to be awkward, but p of y given x given y. We know that every value of x is possible. But only, and every value of y is possible as well. So I think we can just switch these up. feels like cheating. I feel like I want to put the constraints in this model as well, but what would this look like? So I mean, because this feels odd because I'm saying like, what am I going to do with this? This is just some kind of. I mean, this tells me that one way is better than the other one, but I'm already using this knowledge to construct this problem. That was weird, but let's just do it. Let's see how it goes. Let's just make this all. I don't know. 9 1/3. Okay. Y 2x. Typo here. 2x. What's wrong? Oh. Okay, so now we're going to look at, we'll generate some data from the true model. Actually, do the ground truth yet. Okay, so we got our ground truth model. We got our uniform prior 1, prior 2. Let's get data from the truth. If we can just get one data point. So we should get one little data point of that. Let's actually get, I don't know, let's get several data points and look at the sum of the. There we go. What the heck? What does that mean? I've seen that. Okay, let's just call it something else maybe. What does that mean? Didn't it just work? Maybe I shouldn't call these ones. Finance call them ABCs. Or clean this all up. Kidding me? All right. What have I done now? How did that happen? All right, so let's look at the likelihood of this data under model 1. So this score function will give me likelihood. Okay. And then let's look at the model 4. Huh? That's exactly what I did not expect. Yeah, this is wrong. I don't want, because this is looking at the likelihood by using maximum likelihood estimate of the parameters. Can I not score likelihood under these models? Huh, that's actually interesting. Huh, guess not. So that score function only allows me to do it for a given. So this is actually looking at it. It's forcing me to estimate maximum likelihood, but I already have the parameters. But I already have parameters here. So I want to score it under these models. How do I do that? Oh, I'm not even trying to do that. Could do it manually. Feels like a lot of work. So how would that look like? I would say, so likelihood for X is always going to be 1/3. So write some function here. Let's actually just kind of work this out one line by one. Sim data. So what we want to do is take x2y model. Instead, we got model x. Go as a table. All right. I just index this by x1. How does that work? Nope. So when you get, and this is, just do this one. So I get some function that out gives me access to that table. I forgot how you do this in R. I'm out of practice. How do you get the access? Node, parents, children, prob. All right, so we want that prob thing. Yonder peasant, who is he? Okay, so plug that all in there. Is that going to work? Yep. And then we can log all this stuff. And sum them up. All right. Sum log x equals that. Sum log y equals. That's bad. How that happened? Got some infinities in there. I must have. So we're generating y's that have zero probability. X to y model. And just do see, like they look structurally the same. So do I get the same thing if I do truth model? Or do I get getting zeros in there, which can't be true? System data has to have impossible values. Because, I see, because we're not conditioning correctly on X. I'm not sure how to vectorize this, but let's say, so it's a matrix, so I should be able to say 2. Okay, so that gave me 0.5 as expected. So can I vectorize this operation? Vectorization is kind of what makes R fun. So that's my Y, that's my X column. This is my Y column. So we'll know this is not working if we get any zeros. That is not what I expected. So it's expanding it into some matrix. So we're gonna have to do a for loop. Probably an easier way to do this, but I don't know what it is. Not worth looking into. So for how do you do for loops? X for X in data X. Is that enough? For Y in sim data Y. Model Y prob Y in the rows, X on the columns. Let's just print that for now. So basic sanity check, so we shouldn't get any zeros printing out. And we get zeros. How the heck did that happen? Well, in the truth model, we shouldn't get any zeros. That fake model, yeah, all right, so I'm still doing something wrong. For X and sim data X. No, not for Y. No, we went for I and so this is what I'm doing wrong. It's too many number of rows. Sim. X equals sim data X Y. Let's do the arrows. Sim data I R2. This hopefully should work. I did wrong. Come on. Now what? Okay, at least no zeros. Also have no zeros. Great. So we got may as well just use no. Is they have plus equals in R? I don't even remember. What did I do? Okay. No. It is. It's not. Equals. Okay. That seems high. But I guess there's less entropy there, so or more entropy there. So okay. I'm just assume I didn't make any errors, which is probably not true. But let's make this a function. log likelihood. Return some log y plus some log x. And we're in R, so we got to wrap that up. And the all right. Let's just refresh the environment so we don't get ourselves in trouble. All right, so we got ground truth model, model 1, model 2, wrong model. Send some data from the ground truth model. And then we're going to look at this likelihood function. And we're going to look at the of our model, so x to y, x to y model given this data. And then this other thing should have less likelihood. So this should be right, because I'm making this dependent. Okay, so there's a way of doing this, but we're not going to do it the hard way. We're going to do it the easy way. So this would be the same function for model 2, except I guess these would have to be switched. This is way more work than I expected, but okay. All right, that is definitely less than the other. So, okay, so we proved that after way more work than I expected. Let's see if we can't push our way through the rest of these slides. We're over time now, but it's Christmas, so.
And to spell out what this means more formally, if we have this relation R, and we define.
See, what's irritating me about this though is that I had to know, like, how is this useful for me if I already incorporated information, knowledge that X leads to Y. Like, this would be useful if I had no idea if X caused Y or Y caused X, and I was trying to find some likelihood way of kind of encoding that, but it looks like I'm already using causal knowledge here. I mean, unless there's some way of using, you know, the constraints on the constraints on the joint, on the domain, the possible values of X and Y. We'll see. Maybe we haven't gotten to why this is useful yet.
Nx of x is the number of y values that are allowed when this x is given. And likewise, we define ny of y as the number of options for x given y. Then simple computation shows that the prior on the set of xy pairs is given by a quotient of these numbers relative to the total number
on the
of
right
the
page.
domains of this variance.
Oh, right.
And the causal principle is because knowing about the mechanism relating cause to effect is irrelevant at this point. And then assign as above, which is in general a non-uniform prior over R, which captures the asymmetry between cause and effect. Once we have defined such an asymmetric prior, we are able to infer causal directions with some probability by just comparing the corresponding likelihoods. And to spell out what this means more formally, if we have this relation R, and we define nx of x as the number of y values that are allowed when this x is given, and likewise, we define ny of y as the number of options for x given y, then simple computation shows that the prior on the set of xy pairs is given by a quotient of these numbers relative to the total number.
I'm not sure why this is inverted. I'm sure the math. So yeah, okay, we're just kind of looking at, so that what we're doing is getting causal direction by just looking at what numbers are allowed.
Of the domains of this variance. And the causal principle of insufficient reason amounts to preferring causal directions for which many different values of the cause are allowed for the observed value of the effect, but only few different values of the effect are allowed for the observed value of the cause.
Let's say that again. That sounds important. Many different values of the cause are allowed for the observed value of the effect. Only few different values of the effect are allowed. So we would prefer causal directions for which. So we're going to have an inductive bias towards a causal direction where many different values of the cause are allowed for an observed value of the effect. Many different values of the cause. We can get a lot of, so the cause can be whatever it wants, but given the cause, given an effect, we can get a whole bunch of different causes that could have led to that. But given a cause, we only have a few values of the effect that are allowed. Let's just say that one more time because that sounds really cool and really interesting. I want to internalize it. Hold on a second. Right, so many different values of the cause are allowed for the observed value of the effect. So we observe an effect, we observe a cause, and we observe many effects. We observe X and Y. We don't know if X is the cause or if Y is the cause, but if we suppose that X is the cause, we would say for a given value of, let's see if we can actually, oh, I actually forgot to reshare, sorry. Let's go back here. And we didn't miss anything. Actually, let's stay in R. So what we want to see here is that, like, if we see, so sim data diverse. So what we want to see is that, all right, so we know many different values of the cause are allowed for the observed value of the effect. So we say sim data filter y equals 1. Table So we're going to see, we should see a lot of values of, so if we're given a value of y, the effect, we should see a lot of values of the cause. Okay. Let's compare that to x equals 1. Right, so it looks like we have, so actually let's use probability here, prop table. Oh, that doesn't really bite into the tuition. Anyway, let's go back to the video. I was hoping to see something intuitive there, but many different values of the cause are allowed for an observed value. So conditional on the effect, we get a whole big wide range of cause values. But conditional on the cause, we have a narrow range of effect values. Okay, so that sounds like a very useful inductive bias, inferring causal directions. I like it. What out extends to more than 2 variables, but we'll see here. Let's play.
For our mechanical device, this means the following. If we observe the red path, then we consider x causing y more likely, because here we have likelihood 1/3, while for the converse direction, if the ball enters from the bottom, we get 1/6. And remarkably,
So I want to play that again. So he said, from x to y, we get 1/3. What's 1/3? Well, x is 1/3. Here, from y to x, we have why is that 1/6? That was back here. So these probabilities of y, they don't depend on us knowing the causal situation here. So we don't know if the ball is coming from this way or that way. Yeah, I'm not sure I caught that last bit. Let's look at this again. Many different values of x are allowed, but the cause are allowed.
Causal principle of insufficient reason also entails a causal inference principle that we proposed earlier, information geometric causal inference, IGCI, which works for deterministic relations only, the way it was originally phrased. So,
information geometric causal inference, x and y via bijection. Infer if and only accumulate in regions of small f prime rather than small f. So again, this is looking for kind of functional asymmetries in functional causal asymmetries.
x and y are related by a bijection f. Here, in this toy example, it's just a bijection on the intervals 0, 1. Then we infer x causes y if the points accumulate in regions of small slope f rather than small slope of f inverse. And formally, we prefer x causes y if the sum of the logarithm of the slopes on the observed points is smaller than 0. And we will see now that IGCI is just the deterministic and continuous limit of the causal principle of insufficient reason. here we define a relation R by drawing the function f with a fat pen.
So I just want to make sure I understand this again. So we're just saying that if points accumulate in regions of small f prime rather than, right? So this is the inverse. So this is what, right? So why do we assume that we would get a lower slope here? What is that? What is that? We'd get a This is, I'm trying to make this make intuitive sense here, but we're saying that maybe it's like it's almost it takes some energy to change a cause. It takes less energy to. Takes less energy. I'm thinking in terms of energy. It takes less energy to change a cause than an effect. So, like, given a cause, a small change in the cause, we should see a larger change in the effect. I think that's what this assumption is made. It's kind of like an Occam's razor.
And then we discretize the variables x and y. And for each observed point, we consider the quotient of the number of options for y given x and the number of options for x given y. And this quotient is just the slope. And if we now extend this comparison of number of xi of n tuples, then the number of possible n tuples y for the observed n tuple x is given by product of all this nx of xj, and likewise for y, the product of all ny of yj. Therefore, the causal principle of insufficient reason just compares the sum of the logarithms of these numbers, ny of yj, versus the sum of logarithms of nx of xj, which at the end of the day just amounts to computing the sum of the logarithm of the slopes in order to infer the causal direction. The high-level lesson from this example is non-trivial statistical inference rules follow from applying causal principle of insufficient reason to the product space x to the power of n times y to the power of n. And we will see that this is not the only example. Let us look at the usual maximum entropy principle. Let x be a random variable or vector with unknown distribution p, and we are given expectations of some functions fj. Then the best guess for the distribution p is the one that maximizes Stern entropy subject to those constraints. And the analytical solution is given just by an
we only know the so maximum entropy principle. I haven't seen this in a while. We only know the expectations of some functions fj of x. And the best guess for p is the thing that maximizes the entropy of p of x. The distribution that maximizes the entropy of x subject to star. Where's the star even? Oh, wait, some. Oh, so these are just kind of constraints. Analytical solution is given by the so we have okay, so that we can just kind of find lambda and okay, so we have a solution to this. So okay, so this is our distribution, and then we find the lambda and okay, so we're just solving for the lambda and the gamma that maximize something. Anyway, this makes intuitive sense, although I'm just first I'm seeing this lambda and gamma notation. But yeah, we just want to find the most the distribution has the most uncertainty subject to satisfying the expectations of these functions.
Distribution in the exponential family corresponding to these functions. And the prominent example is the Gaussian that maximizes entropy subject to first and second moments. The most important and most relevant justification for our purposes for maximum entropy is the one given by Wallace and Jaynes. It's a combinatorial one by counting the number of combinations given an empirical distribution. So given that x attains values in the set x1 to xk, let nj denote the number of occurrences of xj after n draws. Then the number of realizations is given by this quotient of factorials. And the Stirling approximation shows that asymptotically the logarithm of this number of combinations can be estimated via the entropy of the empirical distribution. Therefore, the entropy of an empirical distribution measures the number of realizations for large n. And accordingly, maximum entropy and principle of insufficient reason are tightly connected because a uniform prior on the product space results with high probability in empirical distributions close to max n. In this sense, max n follows from applying PIR to the product space. But if x causes y, we should not apply usual PIR to the product spaces xn times yn. Instead, we should use causal PIR. And we will see that this yields a different maximum entropy principle, namely the causal maximum entropy principle, which reads as follows. If x causes y, we first obtain P of x by maximizing the entropy of x, subject to all constraints for x. And then we obtain P of y given x by maximizing the conditional entropy of y given x, subject to all joint constraints. This has been postulated by us without a formal justification.
Basically saying like, okay, we're just gonna maximize entropy in these distributions. We don't know anything, subject to every constraint that we know on the system. And those constraints could come from causality.
A little bit later, we provided a physical toy model that justifies it to some extent, because there the order of the entropy maximization corresponded to the order of a mixing process in a thermodynamics scenario. I can't go into details here. But the main argument given by us back then was that it just results in more plausible distributions. So if you have a binary variable x and a real valued variable y, and you're given just the first and second moments, then for x causing y, causal maximum entropy results in a Gaussian mixed model, where the two modes of y correspond to the two values of the binary. On the other hand, for y causing x, y is a Gaussian, and P of x given y is given by a sigmoid function. And we see that the binary x only induces two modes of y if it's the cause, which is plausible. The usual maximum entropy is implausible because maximizing joint entropy results in P of y being a mixture of two Gaussians, regardless of the causal directions. And this is implausible because there's no reason why the variable y should get bimodal just because it has an influence on a binary variable. This violates the independence of mechanisms in the sense that the variable y should not know anything about the relation to the effect, the binary effect. Similar paradoxes entailed by usual maximum entropy for cause-effect relations were already described by Hunter and Pearl quite early.
Okay, so now he's going inside baseball. I'm just going to kind of peruse the end. But what he's saying here is that he's now formalized some kind of earlier initial ideas they have of this independence and mechanism stuff, which is just to say that you know, if y is a cause of x, then the parameters or the distribution of probability of y given x shouldn't give you any information about the probability of y. But if you were to kind of fit the model x is y as being a cause of x, you would see that's being violated empirically in the data. You would see this, you would see some information being exchanged between the probability of y given x and the probability of x. And so they're kind of going down, formalizing these ideas a bit more. And these are actually, I think these are particularly useful. See, so this is interesting to me from let's actually see his take home, and I'll kind of add some.
And the idea is always that maximizing the joint entropy favors realizations of the cause that admit more realizations of the effect. The high-level take-home message reads, we have a sort of inductive bias that prefers causal models, for instance, directions, tags, structural equations, for which the observed effect admits more values of the cause, and the observed cause admits only few values of the effect. It would be challenging to translate that into modern learning approaches, for instance, variational autoencoders or whatsoever. I should also mention that generalization to tags with n variables is non-trivial because there's not a unique order.
So what's interesting about this is to say that within machine learning, we would like to be able to. So in causal modeling, you have to specify a DAG, and that DAG requires some kind of domain knowledge to say, okay, well, based on my domain knowledge, this is what the causal structure of the system looks like. And folks in machine learning don't like doing that. It's not that they don't. My experience is it's not so much that people are afraid of using domain knowledge on a problem, but rather they don't want to have to create bespoke problem models for each problem. Rather, they would like to have some kind of learning architecture with the right inductive biases, such that given data, it can learn the causal structure it needs to learn from the data. Now, if you kind of stick to traditional structured learning methods, you can only really learn data classes of data. So what that means that you really couldn't use data to figure out the difference between X causes Y and Y causes X. Here, this is giving you a way to do it. And so this is interesting because it would say like, well, let's suppose that we had some kind of, I don't know, neural network architecture with a certain inductive bias, a certain architectural property that encoded this inductive bias. Say, for example, well, I don't know. I don't know how you would do that. Perhaps graph neural nets. I don't know. But like, if you can encode that inductive bias, then it could, in theory, learn causal structure from observational data, and then continue on to make causal inferences from that data set.
And I should also admit that the presentation ignored an important problem, namely the question, where does the constraint X, Y is in R come from?
Of course.
There are two different sources of knowledge that we should distinguish, actually. First, there could be knowledge about that particular observation. For instance, a coarse-grained measurement of the outcome told us that the pair XY is in R without telling us the exact values of X and Y. Or on the other hand, there could be structural insight telling us that there's a mechanism that generates only XY pairs in R. And I can't go into details here, but our arguments were implicitly based on the latter. So implicitly, I was always assuming structural insight, for instance, for the mechanical device. But to justify that to some extent, I postulated a principle, bias for structural insight, that reads any constraint R that reduces the logarithm of number of possible outcomes by far more than the description length of R indicates an underlying mechanism that renders outcomes in R likely. And to explain the idea, we just consider a thermodynamic scenario. If we know that all molecules of a gas are inside a certain volume, then this only happens because there is a wall that confines the gas. It never happens by chance.
Right.
So this is an example for a constraint that reduces the number of options drastically, although the constraint has a short description length. And this happens quite often. Maybe this is something to think about. Thanks for your attention.
So that was cool. Like I said, so I read that because I'm really interested in this Jan Singh's line of research, which is often taking ideas from algorithmic information theory or sorry, I guess you would call that algorithmic complexity theory and thermodynamics, and trying to apply them to causal models to try to come up with these inductive biases that are that are inductive biases that we could use in machine learning to potentially build in architectures that could learn a causal model from observational data on the way to performing some causal inference query. And I think there's some that's actually really promising in terms of whether or not, if you're using probabilistic programming, you're using neural nets of kind of coming up with universal models for causal reasoning that don't require you to pre-specify a DAG from domain knowledge, because you could simply learn that information from the data. I don't know exactly how an inductive bias like this would be encoded in a neural net architecture. Something tells me perhaps, I don't know, graph neural nets, or maybe some of that new work in kind of combining neural networks with differential equations. I don't know. I'm just kind of spitballing because that's kind of what my gut is telling me. But probabilistic programming, it seems that this would be actually pretty easy to do. Yeah, cool. And of course, they say like generalization to n variables is non-trivial. Yeah. But got to start from somewhere. All right. Well, that's all she wrote for me for today. Thanks for tuning in or watching this recording, and Merry Christmas.